Thermodynamics looks at the interaction of internal energy, heat transfer, and work in chemical reactions. This video is going to look at problems that deal with three specific topics: the specific heat, latent heat, and then calorimetry. Specific heat is the amount of heat needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. So a substance that needs a lot of heat transferring into it in order to see a raise in temperature will have a high specific heat. A substance that very quickly responds to heat moving into it with a change in temperature will have a low specific heat. The specific heat of water is 4.184 joules per gram Kelvin. You may also see this unit as joules per gram degree Celsius. Either one can be used, and they're pretty much interchangeable because the size of a Celsius degree and a Kelvin unit is exactly the same. The equation that you use for specific heat, you also use for calorimetry problems, which we'll talk about later in the video. And it says in order to find Q, because Q again represents the heat being transferred, Q can be calculated if you know the mass, that's the M, the specific heat, that's C, and the change in temperature, delta T here meaning the change in temperature. To calculate the change in temperature, you take the final temperature of your system when the reaction is done and subtract from it the initial temperature. So it's T final minus T initial. If you write it out as a math problem, you notice that it's F and then I. It's in alphabetical order, so you can just file that away to remember which one you're subtracting from the other. It is that initial is subtracted from final. A related type of problem are latent heat problems. Latent heat is the amount of heat per unit of a substance required for a phase change to occur, and it's generally expressed as kilojoules per kilogram. When a substance is changing phase, when it's moving from solid to liquid or liquid to gas, the temperature does not change. And so it's sort of a hidden heat. Latent heat is a hidden heat. You don't see that it's being absorbed by a substance until all of the substance has made that phase change. That is why you can calibrate a thermometer in a beaker of icy water, because the ice and the water have reached thermal equilibrium, so they will be at 0 degrees Celsius, and that water will stay at 0 degrees Celsius until all of the ice has melted. The equation for latent heat is Q, again we're looking at heat transfer, equal to M for mass times L, which is your latent heat constant. And there are three types of latent heat constants. The latent heat of fusion is dealing with the transition of a solid into a liquid. Vaporization is when you're going from a liquid to a gas. And the latent heat of sublimation, those values are needed for when a solid goes directly into the gaseous state. So here's an example of a problem that's going to ask you to figure out something related to specific heat and latent heat. It asks how much energy, in this case heat, is needed to change 200 grams of diethyl ether from 5 degrees Celsius to 35 degrees Celsius, which is its boiling point, and then boil it at its boiling point. And while it is boiling, of course, it is changing slowly molecule by molecule from liquid to gas. The constants are given, the specific heat for diethyl ether and the latent heat of vaporization. And so you just need to use the formulas and plug them in. So here's our specific heat formula. We have the mass of water, or not water, diethyl ether, 200 grams, the specific heat, and how much did the temperature change. We're going from the final temperature of 35 degrees Celsius, subtract from that the initial temperature of 5 degrees Celsius, that gives you 30 degrees temperature difference, and 30 degrees Celsius is the same amount of size of temperature difference as 30 Kelvin, so you can just change the units once you've got the temperature difference. If you go ahead and do the math, you get 13,980 joules, or we'll put that into kilojoules, 14.0 kilojoules. Now you've got it to boiling at 35 degrees Celsius. Now you need to boil it. You need to have it vaporized. So you use the latent heat formula, and again plugging in the mass of 200 grams, and here we have our latent heat of vaporization. The constant is given to you as kilojoules per kilogram, so we just need to drop that down into joules per gram, which is a very easy conversion, and then do the math to find out that that will take 71.4 kilojoules. And of course, going from a liquid to a gas is going to require a lot of heat moving in, a lot of energy transfer to make that change of phase. So when you add these two together, the total amount of heat needed, or the final Q, would be 85.4 kilojoules. Where do we get these values for specific heat or latent heat? Well, they happen through the process of calorimetry. And in calorimetry, we're measuring the amount of heat released or the amount absorbed during a chemical reaction. We typically do that by measuring the temperature change of the surroundings. Remember that we're dealing with how a system is affecting its surroundings, how heat is moving between a system and its surroundings. And so we're often measuring the surroundings when we're doing calorimetry. You need to think about two equations in calorimetry. The Q equals mc delta T again. This equation, will be your friend. But you also need to think about the relationship between the system losing energy and the surrounding gaining energy, or vice versa. So if we've got a system losing energy, its heat Q will be equal to a negative of what's being gained by the surroundings. The value will be the same, so if this is 1,000 kilojoules, this will also be 1,000 kilojoules. But one of them will be negative, because negative is going to be the amount showing that heat is being released, and one will be positive, showing that heat is being absorbed. So that when heat is lost, it's giving a negative value. When heat is being absorbed, it is a positive value. We see that again when we go on to endothermic and exothermic reactions. Negative means exothermic, heat goes out, and positive is endothermic. So here's a problem that deals with calorimetry, that a 25-gram piece of hot metal, which is at 97 degrees Celsius, is plunged into a cup of cool water, and temperature changes until they are both reach thermal equilibrium at 22 degrees. The hot metal goes from 97 to 22, the cool water goes from 19 to 22. So how do you calculate the specific heat capacity of the metal? Well, you use the Q loss equals the negative of Q gained, and I forgot to add in here, but instead of Q, we're just going to break out and use the MC delta T on both sides of the equal sign. So here's my MC delta T for my Q lost, which is 25 grams of metal, unknown specific heat, and a negative 75 K temperature change, because our final temperature was 22 degrees, our initial temperature was 97, and that makes negative 75. And then on the Q gained, we need to use a negative of it, so we have a negative of, and again our MC delta T, here's the mass, specific heat of water, temperature change of only 3 degrees in this case because it was just going from 19 to 22. If you go ahead and do the math and solve for X, we find a specific heat of 0.234 joules per gram Kelvin. And this is fairly typical of metals. Metals have a low specific heat, showing that they change temperature quickly, whereas water has a high specific heat. It takes a lot of energy to get water to change. This is advantageous for living things that are made up primarily of water. It helps us keep our temperature stable, the fact that we're made up of water, that you have to put in a lot of heat energy. Imagine if we were all robots, we wouldn't do very well under the noonday sun. So this covers what I want to talk about on these three types of equations that are all having you solve for Q, looking at how heat is being transferred in different reactions.